I'm Madhur, and today I will do a problem in hypothesis testing. And the problem goes like this. Hope you can see it. If not, as long as you can hear me, this should be okay. All right. So the zone of inhibition of vancomycin against MRSA is 19.5 millimeter with standard deviation of 2.1 millimeter. A pharma company claims that they have developed a new drug named Mistokiller, which works better than vancomycin and MRSA. A lab tech at CDC, Central of Disease Control, collected 32 samples from 32 different city hospitals, which therefore means random samples of MRSA to test and found that mean of zone of inhibition of Mistokiller to be 20.1 millimeter. Now, the question is, does this prove that Mistokiller is better than vancomycin that is available in the market currently? Um, so first of all, let me go over a few of these terminology. Probably you guys don't know this. The reason I picked this problem was because I did these kind of things in my microbiology lab undergrad. So, okay, so this in the middle, the shaded, the circle thing is Mistokiller. You kind of like place the pills of medicine at the center, and this is a petri disk in which you have agar, which is agar is pretty much a food for bacteria or viruses, and you are pretty much growing. You're growing bacteria in this MRSA. I'm pretty sure you guys know what MRSA is. If not, it stands for methicillin-resistant Staphylococcus aureus. Methicillin is a form of it's a penicillin, a different kind. So methicillin resistance means the Staphylococcus aureus is resistant to that medicine, so it means it doesn't work. That's why next they came up with those vancomycin, which normally works for MRSA. Um, Now, zone of inhibition, what that is when you place the pill in the middle, it starts to kill the bacteria around it. So the clear area is the zone of inhibition, and these you say at the corner there is still bacteria is still alive. Of course, I could have mentioned more things like how long it was kept and what temperature. So there are lots of things that the person who is doing test right will have to keep in control. But of course, I don't have time to talk about all that. So skipping that out, which of course you don't need to do that anyway, because focus is on hypothesis testing. So now, to get started on the hypothesis testing, first part, this is test for mean, not for proportion or standard variance. Okay. And the next thing, if you can, as you can see, sample size is bigger enough, well, bigger than 30. And also, the population standard deviation is given. Therefore, we will use z-test. And I stated the null hypothesis and alternate hypothesis right here. Didn't have enough space. I wanted to like try to fit everything here. Okay, so I'm using this. Sorry. Null hypothesis is that saying that the mean is 19.5 millimeter, which of course is the normal, the regular one, and mean, which means like zone of inhibition is 19.5 millimeter. However, the alternate hypothesis is the claim part, right? So that they are claiming that is better, hence greater than 19.5 millimeter. Of course, we could have used that. We could have covered both bases. I don't think that's technically incorrect. If you do that, you could have said that, okay, it's not equal to, therefore you could have done the test on the two-tail test. However, I have done one-tail test because even that's technically correct, but in real life scenario, right, you wouldn't do it because if you are the one who was coming up with all these kind of research, or you're doing the testing and you go to your boss saying that, hey boss, I have this idea and I want to do testing. Can I get the money? And I'll be out of my office for so many days because it takes lots of time and money. And your boss was not going to be happy because you are wasting your money and time on something you don't really have to do. Because all you have to do is you're trying to prove it's better, not worse. So why would you go waste your time and money to do? Because it actually if we actually do the sampling and all that part, it takes lots of time if you actually control the environment, control the temperature, avoid the contamination and all that, right? I hope that makes sense. All right. Now, just statistics we are using is z star equals to x bar, which is sample mean minus population mean divided by standard deviation population divided by square root of n, sample size. In this case, we have 2, and I'm pretty sure that's pretty much I'm plugging in whatever is given on the problem. I think that's clear. So I got 1.616 after calculation. I'm pretty sure you guys know how to use calculator. I hope so. Then I have, okay, of course. In the problem, it wasn't told what confidence interval you should use or what alpha is. So, and most commonly used is 95%, and that's what I used here. Since it's one-tail test and 95% confidence interval, we have alpha equals to 0.05. And our conclusion is, since what we got here, z star after calculations 1.616 is less than 1.645, which is a critical point. And you can look at here as well. I got this number from the book, of course, for one-tail test, but of course you can also use a calculator to find this. And if you look at the distribution diagram here, the whole thing under the curve is 1%, 100%, 1, P, probability 1. And NRR, non-rejection region, is shaded 95%, and the rejection region is the other side, not shaded part. And what splits 2 is critical point, where z equals to 1.645. And our 1.616 is, since we start, okay, right hand side is positive, z, left hand side from the mean is negative. So we only care about that side in this case. Therefore, go in that direction. If 1.645 is here, since 1.616 is less, he has to be in the non-rejection area. It's clear, right? Therefore, we fail to reject the null hypothesis. Again, we fail to reject null hypothesis, not alternate hypothesis. Because everything we're doing is for a null hypothesis, okay? So, and however, does that mean that this proves or disprove that the Mystic Killer is better than vancomycin or vancomycin is better? No, it doesn't. All we are saying here is we don't have enough evidence to support the claim of pharma company that the Mr. Killer is actually better than vancomycin. That's all we are saying. We're not saying that we disprove null hypothesis either, okay? Now, few things that will affect our result value here, and of course, because if this changes, of course, our conclusion will also change, right? If this turns out to be greater than 1.645, we'll reject the null hypothesis based on this confidence interval, of course. So, if we have sample mean different, how could we get different sample mean for many reasons? For example, if the data collection is not done well or done differently next time, if you collect a different sample, it will change our sample mean. Or if you because of the contamination, you could get different values. You could be biased. Let's say you're lazy to go different places to collect samples, so you just collected everything from like one place, and that doesn't represent the whole population, or whatever, easily accessible. That's what you used, or you're trying to save money, so you didn't do whatever the right thing was to do. to get a good sample. You didn't do that. That's why so sample collection could change your mean of sample x bar, and if that changes, of course, you'll get different value, especially for when the n is only 35, 32. Sorry, this is not big, so there will chances are they will definitely probably change, give you a different value here. And also another thing, of course, the population mean is going to stay same. Population standard deviation is going to stay the same. However, once you change the sample size, it will change your this value again, g star again, and therefore well, we may get different conclusion as well. For example, if we uh, raise our sample size, if we make sample size bigger, we'll get a smaller margin of error. And if we keep the same confidence interval, the smaller margin of error will give a different g value, g value, right? Another thing is what if we change the confidence interval? Here we are only using 95%. However, if we're using 90%, and I believe 90% is a lot less than 1.616, we will end up rejecting the null hypothesis in that case. However, if our value z star was even bigger than 1.616 and even bigger than bigger than critical, not critical point, bigger than 1.645, and we were using 99% confidence interval, which would be somewhere here. I think the value is 1.9 something, which is, and we will still be rejecting because the cutoff point is below the on the left hand side of the cutoff point. Let me just see if I forget to explain anything here. I don't think so. Okay, I hope that was helpful. If you have any question, don't ask.